I want to make a claim that will sound wrong. Not approximately wrong, not wrong in some technical or pedantic sense, but straightforwardly, obviously wrong to anyone who has taken a physics class or read a popular science book. The claim is this: the speed of light is not a speed. Before you dismiss this, let me tell you what I do not mean. I do not mean that light does not travel. It does. I do not mean that there is no number associated with how light propagates through space. There is, and that number is approximately 299,792,458 meters per second. I do not mean that measuring the speed of light is meaningless, or that the experiments of Ole Romer, who first measured it in 1676 using the moons of Jupiter, were misguided. What I mean is something specific and precise. The speed of light, c, has a role in the laws of physics that is fundamentally different from the role played by any other speed. It is not a property of light in the way that the speed of sound is a property of the medium through which sound travels. It is not a measurement that depends on the conditions of the experiment. It is a conversion factor, a constant of nature that tells you the relationship between space and time that is built into the geometry of the universe itself. And once you understand what c actually is, the claim that nothing can exceed the speed of light takes on a completely different meaning from the one you were probably taught. The statement "nothing can travel faster than light" is one of the most famous results in physics. It appears in every popular account of special relativity. It is often presented as a prohibition, as if nature has posted a speed limit and enforces it with cosmic traffic police. But this framing misses the deep reason for the limit, which is not a prohibition at all, but a geometric fact about the structure of space-time. I want to take you through the full argument, because understanding why c is not really a speed requires understanding what space-time actually is, what the space-time interval actually measures, and why the impossibility of exceeding c is equivalent to the impossibility of rotating a line in a plane by more than 90 degrees. When you see the geometry, the speed limit becomes something different, not a restriction on the possible, but a statement about the structure of the possible. Let me start with the question of what a speed actually is. In classical mechanics, the speed of an object is the rate at which it changes its spatial position. Speed equals distance divided by time. This definition is operational, meaning it tells you how to measure speed. You measure how far the object moved and you divide by how long it took. The result is a number with units of distance over time, meters per second. The speed of an object is a relational quantity. It is the speed relative to something. A car moving at 100 kilometers per hour is moving at 100 kilometers per hour relative to the road. The same car is nearly stationary relative to a car moving at 99 kilometers per hour next to it. Speed is always speed relative to a specified reference frame. There is no such thing as absolute speed, as Newton established. Now consider the speed of light. In the 1860s, Maxwell's equations for electromagnetism predicted that electromagnetic waves propagate at a specific speed, c equals 1 over the square root of mu naught epsilon naught, where mu naught is the permeability and epsilon naught is the permittivity of free space. The predicted speed was approximately 3 times 10 to the 8 meters per second, consistent with measurements of the speed of light. Maxwell concluded that light is an electromagnetic wave, but there was immediately a conceptual problem. Maxwell's equations predict a specific speed for light without specifying what that speed is relative to. In 19th century physics, the natural answer was that Maxwell's equations apply in the rest frame of the luminiferous ether, the medium through which light was assumed to propagate. The speed c was the speed of light relative to the aether. The Michelson-Morley experiment of 1,887 showed that the speed of light is the same in all directions regardless of Earth's motion, demolishing the ether hypothesis. Einstein took the result seriously and made it a postulate. The speed of light in vacuum is the same for all inertial observers, regardless of the motion of the source or the observer. This postulate has an immediate and radical implication. If c is the same for all observers, then c is not a speed in the ordinary sense at all. An ordinary speed depends on the reference frame. The same object has different speeds in different frames. A speed that is the same in all frames is not measuring the motion of something relative to a reference frame. It is measuring something more fundamental, something about the structure of space-time itself. What is that something? To answer this question, I need to introduce the space-time interval, which I described in the distance illusion video. The space-time interval between two events is s squared equals minus c squared delta t squared plus delta x squared plus delta y squared plus delta z squared. This quantity is invariant under Lorentz transformations. All observers, regardless of their relative motion, agree on its value. The invariance of the space-time interval tells you that c is the conversion factor between the time axis and the space axes in space-time. It tells you how to combine a time separation and a spatial separation into a single geometric distance in the four-dimensional space-time manifold. It is not the speed of any specific object. It is the scale factor that makes time and space commensurable. If this is already shifting your understanding of something as fundamental as speed and time, there are 12 principles that take this kind of insight further. Ready to change how you see the world? Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. Let me develop the geometric picture because I think it is the clearest way to see why c is not a speed. Consider ordinary two-dimensional space, a plane. The distance between 2 points is given by the Pythagorean theorem, d squared equals delta x squared plus delta y squared. This distance is invariant under rotations of the coordinate system. If you rotate your x and y axes, the components delta x and delta y change, but the combination d squared does not. Now compare this to the space-time interval. S squared equals minus c squared delta t squared plus delta x squared. The interval is invariant under Lorentz transformations in the same way that Euclidean distance is invariant under rotations. Lorentz transformations are the rotations of space-time. The crucial difference from ordinary Euclidean geometry is the minus sign in front of the time component. This minus sign means that space-time is not Euclidean. It is what mathematicians call a pseudo-Riemannian space with Minkowski signature. The minus sign has profound geometric consequences. In Euclidean space, the distance between 2 points is always positive. D squared is always greater than or equal to 0. You can rotate between the x and y directions continuously. There is no preferred direction. All directions are equivalent. In Minkowski spacetime, the interval s squared can be positive, negative, or 0. Positive s squared means space-like separation. The spatial part dominates. Negative s squared means time-like separation. The temporal part dominates. 0s squared means light-like separation. The space-time path is a null geodesic, the path of a light ray. The minus sign divides space-time into 3 distinct sectors: the past light cone, the future light cone, and the space-like region outside the light cones. These sectors are geometric features of the space-time structure, not arbitrary classifications. The light cone is the boundary between the regions that can causally influence an event and the regions that cannot. Now here is the geometric fact about C. In Minkowski spacetime, just as in Euclidean space, there are preferred directions. But unlike in Euclidean space, where all directions are equivalent, in Minkowski spacetime there are three distinct types of direction: time-like, space-like, and null. The null directions are the ones along which s squared equals 0. These are the light cone directions. The speed c is the slope of the light cone in spacetime, the ratio of distance to time along the null directions. An object moving through spacetime traces out a world line. The world line of an object at rest is a vertical line, pointing in the time direction. The world line of an object moving at constant velocity is a tilted line. The faster the object moves, the more tilted the world line. The world line of a massless particle, a photon, lies exactly on the light cone. It makes a 45-degree angle with the time axis when you draw space-time with time in one direction and space in another, with units chosen so that c equals 1. Can a world line be more tilted than the light cone? That would mean the world line is more horizontal than diagonal in the space-time diagram, meaning the object moves more distance in space than the product of c and the time elapsed. In Minkowski geometry, this corresponds to a space-like world line, a curve that is entirely in the space-like sector where s squared is positive. A space-like world line is not a valid trajectory for any massive object. This is not because of a speed limit. It is because of what a world line means. A world line is the set of events in space-time that constitute the existence of an object. For a world line to be a valid physical trajectory, it must be possible for an observer to travel along it, meaning there must be a rest frame for the object at each point. A rest frame for an object is a reference frame in which the object is momentarily at rest, meaning the world line is locally time-like. A space-like curve has no rest frame. There is no reference frame in which the object is at rest along a space-like curve, because the curve is more horizontal than the light cone, and you cannot reach the horizontal axis by any Lorentz transformation. Lorentz transformations tilt the time axis but cannot rotate it past the light cone. This is the geometric reason why nothing can exceed the speed of light. It is not that c is a speed limit in the sense of a maximum allowed value for some continuously variable quantity. It is that the light cone is the boundary between the time-like and space-like sectors of space-time, and physical objects can only have time-like world lines. The light cone boundary corresponds to zero rest mass. Massless particles travel exactly at c, and massive particles travel at speeds less than c. Nothing travels at exactly c except massless particles, and nothing travels faster than c because the space-like region has no rest frame. The speed of light is not a speed limit any more than the edge of a two-dimensional surface is a speed limit on a marble rolling on the surface. The marble cannot go off the edge, not because of a law preventing it, but because off the edge is not part of the surface. The space-like region is not reachable by massive objects, not because of a prohibition, but because it has no time-like direction, no rest frame, no physical meaning for the trajectory of a massive particle. Let me develop the geometric picture, because I think it is the clearest way to see why c is not a speed. Consider ordinary two-dimensional space, a plane. The distance between 2 points is given by the Pythagorean theorem. D squared equals delta x squared plus delta y squared. This distance is invariant under rotations of the coordinate system. If you rotate your x and y axes by angle theta, the components delta x and delta y change, but the combination d squared does not. Rotation mixes the two spatial directions, but preserves the total distance. Now compare this to the space-time interval. S squared equals minus c squared delta t squared plus delta x squared. The interval is invariant under Lorentz transformations in the same way that Euclidean distance is invariant under rotations. Lorentz transformations are the rotations of space-time. The crucial difference from ordinary Euclidean geometry is the minus sign in front of the time component. This minus sign means that space-time is not Euclidean. It is what mathematicians call a pseudo-Riemannian space with Minkowski's signature. This sounds technical, but the physical consequence is simple and profound. In Minkowski space-time, not all directions are equivalent. There are three fundamentally different types of direction, and they cannot be continuously transformed into each other by any Lorentz transformation. In Euclidean space, a rotation can continuously rotate the x direction into the y direction. You can rotate by any angle from 0 to 360 degrees and continuously trace a path from one direction to the other. All directions are equivalent, and the rotation group acts transitively on the space of directions. In Minkowski spacetime, a Lorentz boost, which is the spacetime analog of a rotation, can tilt the time axis toward the light cone but never past it. The time axis of a moving observer tilts toward the light cone as the velocity increases. At velocity v, the time axis makes an angle arctan of v over c with the stationary time axis. At velocity c, this angle would be 45 degrees, aligning the time axis with the light cone. But the angle can never actually reach 45 degrees because that would require infinite energy for a massive object. The time axis can approach the light cone asymptotically but never reach it. This is the geometric content of the speed limit. You cannot rotate a time-like direction into a space-like direction by any Lorentz transformation. The time-like directions, the space-like directions, and the null directions of the light cone are three distinct geometric categories that no physical transformation can mix. The boundary between them is the light cone, whose slope is determined by c. Let me describe the light cone more carefully, because it is the central geometric object in all of special relativity and general relativity. At every event in space-time, there is a light cone. The light cone is the set of all null directions from that event, the directions along which a light ray could propagate. It divides space-time into three regions: the interior of the past light cone, which contains all events that could have causally influenced this event; the interior of the future light cone, which contains all events that this event can causally influence; and the exterior of the light cone, the space-like region, which contains events that have no causal relationship with this event. The light cone is a physical structure, not a coordinate artifact. Different observers with different velocities will draw different coordinates on space-time, but they all agree on which events are inside the light cone and which are outside. The light cone is the one geometric object in space-time that all observers agree on. This is why C defines the causal structure of the universe. The light cone determines causality. The light cone is determined by C. Change C and you change causality. An infinite C would mean an infinitely open light cone. Every event would be in causal contact with every other event. A finite C creates the cone structure that separates the causal past from the causal future and from the causally unconnected present. An object moving through space-time traces out a world line. The world line of an object at rest is a vertical line pointing in the time direction. The world line of an object moving at constant velocity is a tilted line. The faster the object moves, the more tilted the world line toward the light cone. For a massive object, the world line is always inside the light cone, always time-like. At every event along its world line, the object's velocity is less than c, and the world line direction is inside the cone. The object has a well-defined rest frame at every event. Its proper time is the time experienced by a clock traveling with it, and it is always positive and finite. For a massless particle, like a photon, the world line lies exactly on the surface of the light cone. It is a null geodesic. The space-time interval along this world line is 0 for every segment. The photon has no rest frame, no proper time. Can a world line lie outside the light cone in the space-like region? Such a world line would be more horizontal than diagonal in the space-time diagram. It would represent an object that moves more distance in space than c times the elapsed time. This is what we mean by superluminal travel. A space-like world line has no rest frame. There is no Lorentz boost that makes the world line vertical. This means there is no reference frame in which the object is momentarily at rest at any event along the space-like world line. The object has no local proper time. Its existence from one event to the next has no locally defined time ordering. In fact, for a space-like interval, the temporal ordering is reversed in some reference frames. What one observer calls the start of the object's journey, another observer calls the end. This temporal reversal means that a superluminal particle would, in some reference frames, travel backward in time, constituting a violation of causality. This is the deepest reason why superluminal travel is impossible for physical objects. It would reverse the causal ordering of events and allow signals to arrive before they were sent. The prohibition is not a speed limit, it is a causality requirement. And the causality requirement is itself a consequence of the geometric structure of Minkowski spacetime, which C defines. Now let me take you to what C actually is at its deepest level, because the geometric picture reveals something that the speed limit framing completely misses. The quantity c appears in the space-time interval as the conversion factor between the time coordinate and the space coordinates. In the interval, s squared equals minus c squared delta t squared plus delta x squared. The factor c squared converts the units of time to the units of space. If you measure time in seconds and distance in meters, you need c squared meter squared per second squared to make the units work out. This means c is telling you something about the relationship between space and time as geometric dimensions of the space-time manifold. Just as the scale of a map tells you how many meters on the ground correspond to 1 centimeter on the map, c tells you how many meters of spatial distance correspond to 1 second of temporal distance in the geometry of space-time. In the natural units that physicists often use, c is set equal to 1. When c equals 1, you can measure time in meters. 1 second of time is equivalent to approximately 3 times 10 to the 8 meters of space. The space-time interval becomes simply s squared equals minus delta t squared plus delta x squared, with all quantities measured in the same units. Time and space are just different directions in the same four-dimensional geometric structure with a sign difference that reflects the Minkowski signature. The value of c, approximately 299,792,458 meters per second, reflects the units we happen to use for measuring time and distance. We chose to measure distance in meters based on the size of the Earth and time in seconds based on the rotation of the Earth. Given these choices, the conversion factor between time and space in the space-time geometry turns out to be 299,792,458 meters per second. If we had chosen different units, we would get a different number. This is why the International Bureau of Weights and Measures in 1983 defined the meter in terms of the speed of light. 1 meter is the distance. Light travels in 1 over 299,792,458 of a second. This definition makes c exactly equal to 299,792,458 458 meters per second by definition, with no experimental uncertainty. The speed of light is no longer a measured quantity. It is a definition, which is exactly what you would expect if c is a conversion factor rather than a speed. What we are really talking about is one of the deepest principles in physics, the unity of space and time. The way c works as a conversion factor between dimensions is the kind of principle that changes how you think about reality at every scale. These are the kinds of transformative ideas I collect in my book. Get 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. Let me now develop the implications of this picture for the concept of time. Because if c is a conversion factor between space and time, then the statement "nothing can travel faster than light" becomes a statement about the geometry of the space-time block. In the block universe, which I described in detail in the permanence of the past video, all events at all times exist with equal reality as features of the four-dimensional space-time structure. Your world line is a specific path through this block, from your birth to your death, parameterized by the proper time you experience. The proper time is the time measured by a clock traveling with you. The proper time along a world line is related to the space-time interval by proper time squared equals minus s squared over c squared for a time-like separation. A moving clock runs slower than a stationary clock. The proper time elapsed is less than the coordinate time elapsed by the Lorentz factor gamma. This is time dilation. Time dilation is a direct consequence of the geometry of space-time and the role of c as the conversion factor. When you move through space, you are trading some of your travel through time for travel through space. The total space-time interval is fixed by the invariant, and if you use some of it for spatial travel, there is less left for temporal travel. Your clock, which measures proper time, runs slower because you are covering less of the time direction per unit of space-time interval. This is the most counterintuitive formulation of special relativity, but I think it is the most clarifying. Movement through space is not free. It comes at the cost of movement through time. The faster you move through space, the slower you move through time. At the maximum possible speed, c, all your movement through the space-time interval is in the spatial direction and none in the temporal direction. Your clock would stop entirely. This is why massless particles, like photons, do not experience time. Their world lines are null geodesics with zero space-time interval, and there is no clock that can be defined for a massless particle. A photon emitted from the Andromeda galaxy 2.537 million years ago arrives at Earth tonight. From Earth's perspective, the photon traveled 2.537 million light years in 2.537 million years. From the photon's perspective, which is not a standard reference frame but can be approached as a limiting case, the journey took zero proper time and covered zero proper distance. The emission and absorption events are at the same location at the same time in the photon's geometry. The photon does not experience the journey at all. This is the ultimate expression of c as a conversion factor rather than a speed. The photon does not travel at the maximum possible speed while experiencing a journey. It does not travel at all in any meaningful rest frame sense. It exists at two events in space-time with zero interval between them. The concept of speed, which requires a moving object and a time elapse, does not apply to the photon. Now let me take you to the most important practical consequence of c being a space-time conversion factor rather than a speed: the causal structure of the universe. The light cone, which I described earlier as the boundary between time-like and space-like separations, defines the causal structure of space-time. An event can only influence events within its future light cone, events that can be reached by a signal traveling at or below c. An event can only be influenced by events within its past light cone, events from which a signal traveling at or below c can reach it. Events outside the light cone have no causal connection to the event at the apex. They are separated by a space-like interval. No signal, no influence, no causal connection is possible across a space-like interval. This is an absolute prohibition, but it is not a speed limit in the sense of preventing something that could otherwise happen. It is a statement about which events are in what part of the space-time geometry. The causal structure of space-time, determined by c, is what makes the concept of cause and effect meaningful. If c were infinite, all events would be in causal contact with all other events, and cause and effect would lose their temporal ordering. An event could be caused by a future event. The arrow of time would have no physical basis. Finite c creates the light cone structure that separates the past from the future, that makes cause precede effect, that gives time its direction. The fact that c is finite is not a limitation. It is what makes the universe coherent, what makes the temporal order of events physically meaningful, what makes it impossible for a cause to occur after its effect. Everything we have been discussing, the geometry of space-time, the role of c as a conversion factor, the way time is a direction in a four-dimensional structure, these are not just abstract ideas. They are principles that reshape how you understand existence itself. I have distilled 12 such principles into my book. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me now develop the implications of this picture for the concept of time, because if c is a conversion factor between space and time, then the concept of time dilation becomes geometrically transparent rather than mysterious. In the four-dimensional space-time block, your world line is a curve. The length of this curve, measured using the Minkowski metric, is your proper time. In Minkowski space-time, the straight world line between two events gives the longest proper time. This is the geometric twin paradox. The traveling twin's world line takes a spatial detour, using up space-time interval on spatial displacement and leaving less for temporal elapsed time. The conversion factor is c. An astronaut moving at 99% of c ages approximately 7 times slower than a person at rest, not because their clock is broken, but because their world line is tilted toward the light cone, using most of the space-time interval on spatial displacement. At c itself, all of the interval is spatial and none is temporal. The photon does not age. Emission and absorption are the same event in the photon's zero-interval geometry. Let me now address the most common misconception about the speed of light that arises from the speed limit framing, which is the question of apparent faster-than-light phenomena. There are several phenomena that appear at first glance to violate the speed of light. Each of them is perfectly consistent with relativity, and understanding why reveals something important about the difference between the speed of something carrying information or energy and the speed of a mathematical construct. The first is the expansion of the universe. Galaxies beyond the Hubble radius, approximately 14 billion light years, are receding from us faster than the speed of light. This is not a violation of special relativity, because the galaxies are not moving through space. They are being carried apart by the expansion of space itself. The speed limit applies to motion through space-time, not to the expansion of space-time. There is no reference frame in which a distant galaxy is moving faster than c relative to a local patch of space. The second is quantum entanglement. When two particles are entangled and a measurement is performed on one, the other particle's quantum state is instantaneously correlated regardless of the distance between them. This appears to be an instantaneous influence, faster than c. But the instantaneous correlation cannot be used to send information faster than c. The measurement outcomes are random, and the correlations can only be seen by comparing the results of both measurements, which requires a classical signal traveling at or below c. Quantum entanglement does not violate the causal structure imposed by c. The third is the phase velocity of light in certain media. In a normal dispersive medium, the phase velocity, the speed at which the phase of a wave moves, is less than c. But in anomalous dispersion, the phase velocity can exceed c. This does not violate special relativity because the phase velocity is not the velocity of energy or information propagation. The group velocity, which is the velocity at which energy and information travel, cannot exceed c even when the phase velocity does. The fourth is the quantum Zeno effect and certain quantum tunneling phenomena. Under some conditions, particles can tunnel through barriers at speeds that appear to exceed c, but careful analysis of these phenomena, taking into account what information or energy is actually being transmitted and at what speed, always shows consistency with relativity. The effective tunneling time is zero or imaginary in the quantum mechanical calculation, but this does not correspond to superluminal information transfer. The fifth is the scissors paradox. If you have a very long pair of scissors and you close them, the point at which the blades intersect moves along the blades at a speed that can exceed c if you close the scissors quickly enough. But the intersection point is not a physical object. It is a geometric abstraction, a mathematical point. No energy or information is being transmitted faster than c. In every case, the quantity that appears to exceed c is not a carrier of energy or information. The causal structure of space-time is always respected. No physical signal, no energy, no information travels faster than c. The constraint is not on arbitrary mathematical constructs, but on physical processes that can transmit cause and effect. Now, let me address the deepest question that the conversion factor interpretation of c raises. Is there any way to make sense of travel faster than c? And if not, why not? In general relativity, the local speed of light is always c. Every local measurement of the speed of light gives c. But there are exact solutions of Einstein's field equations that appear to allow shortcuts through space-time, wormholes, and the Alcubierre metric. Let me describe these and explain what they actually represent in terms of the conversion factor picture. A wormhole is a solution of Einstein's equations that connects two distant regions of space-time through a tunnel. In principle, an object could enter the wormhole at one location and emerge at another location far away without having traveled through the ordinary space between them. From the perspective of the external space-time, the object would appear to have moved faster than c. From the perspective of the object, it traveled through the wormhole at less than c, but the shortcut through the topology of space-time made the effective trip much shorter. The Alcubierre metric, proposed by Miguel Alcubierre in 1994, is a solution of Einstein's equations describing a space-time bubble that moves through space at arbitrary speed. Inside the bubble, a spacecraft is locally at rest. The space in front of the bubble is contracted, and the space behind is expanded, so the bubble moves through space faster than c. The spacecraft inside the bubble has not traveled faster than c relative to its local space-time. The bubble itself has moved through the global space-time at superluminal speed. Both of these solutions require exotic matter, material with negative energy density, to maintain them. No known form of matter has negative energy density, and there are theoretical arguments from quantum field theory that make large amounts of exotic matter very difficult or impossible to produce. Whether wormholes and Alcubierre drives are physically realizable is an open question at the frontier of quantum gravity, which I described in the Aliens video. The important point for our discussion is that even these exotic solutions do not violate the local speed of light. Locally, within any small patch of space-time, the speed of light is always c. The conversion factor between time and space is always c at every point. What these solutions do is manipulate the global geometry of space-time, the topology and the large-scale curvature, to create paths that appear shorter in the global sense than the paths through flat space-time. The conversion factor is still the same. The geometry has been bent. Let me close with what I think is the most important insight about c being a conversion factor rather than a speed. If c is a conversion factor, and if c could, in principle, have any value, what determines the specific value 299,792,458 meters per second? The answer is that the value is not fundamental. It is a consequence of our choice of units. If we measured time in nanoseconds and distance in feet, we would get a different number. The fundamental fact about c is not its numerical value, but its role. It is the conversion factor that determines the light cone structure of space-time, the causal structure that makes temporal ordering meaningful, the scale that connects the time direction to the space directions in the four-dimensional block. The universe has a specific space-time geometry described by the Minkowski metric in flat space-time and by the general relativistic metric in curved space-time. The light cone structure of this geometry is what we call c. In a universe with a different light cone structure, a different value of c, the causal relationships between events would be different. The speed at which physical processes propagate, the rate at which stars burn, the rate at which chemistry occurs, all would be different. But from within such a universe, an observer would measure their local speed of light and find it to be the same. The maximum speed, the boundary between causal and non-causal separations, the slope of the light cone. C is not a speed. It is a feature of the geometry of space-time expressed as a conversion factor in the units we happen to use. Understanding this does not make C less important or less fundamental. It makes it more fundamental because it reveals that what we are really talking about is the causal structure of the universe. And that causal structure is the deepest physical fact about the nature of space and time. We have been exploring one of the most transformative ideas in all of physics, that C is not a speed, but a property of the geometry of reality itself. This is the kind of principle that, once understood, changes how you see everything. I have collected 12 such principles in my book. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. What from today's discussion changed your thinking the most? Tell me in the comments. If this changed how you think about the speed of light, if C looks different after understanding that it is a space-time conversion factor rather than a maximum speed, tell me in the comments. Tell me whether the geometric picture of the light cone as the boundary between causal and non-causal regions illuminates something that the speed limit framing left obscure. Tell me whether you find the photon's zero proper time and zero proper distance between emission and absorption the most striking consequence of the null interval, or whether the definition of the meter in terms of C as a way of recognizing that C is not a measured quantity but a structural constant strikes you more. And subscribe if you want to keep going into the places where the most fundamental constants of nature reveal themselves to be not constants at all, but windows into the geometric structure of reality.